First, I just want to say that I think all the speakers, those who are still here and those who weren't here, did a splendid job. And I think there's very little that I need to add. And that's fine, because my intention was always just to somehow maybe summarize what was done, give some perspective, maybe emphasize some points which might not have been emphasized. But I think a lot has been emphasized. And I think there's really not that much I need to do. Anyway, here are what I take to be some of the most interesting and important things about foundations of quantum mechanics, or even issues more broadly understood, that Bell contributed to. It wasn't just non-locality that he discovered. He played such an important role in finding crucial issues, crucial questions. So I'll begin by just what I intend to do about each of these topics here is just give you a few characteristic quotations from Bell. And if I get through the bottom here and I still have some time, I will come to part 2 of my talk. I don't know how much time this will take. I mean, I will say very little about non-locality because, frankly, so much has been said already. There's no need to say more. So these first 2 items here, hidden variables and non-locality, that I am putting them in that order simply because that seemed to be the logical order of Bell's work. But he first considered the question of hidden variables, and that led him to the issue of non-locality. Then the next 3 items here, and then this one, the fifth one or 6th, whatever number it is, these things are connected in a rather serious, logical way, and I'll try to explain that a little bit. Let me explain the color code. Many of you know the color code. Red is bad, blue is good. Now, for the students, why is that? Why is hidden red?
Because it's not hidden.
Because it tells you nothing.
Because what?
It tells you nothing. It's not clear what does it mean hidden, from who hidden.
Anybody else? Students?
Because you cannot comfort.
Okay, so any case, you will see Bell, I think I have some quote where Bell says he doesn't like that word to talk about hidden variables, and he thinks it's really silly terminology. People have talked about this other bad thing here, naive realism about operators, but you just heard about that, but I don't think this terminology has been used. Okay, let's begin with hidden variables. No, let me begin actually with something which is not even on the list, but really played an important role with Bell's thinking, and this has been stressed by several of the speakers. I mean, you know, people who would like to find either a hidden variable theory, using the bad terminology, or a realistic understanding of quantum mechanics, they're often criticized by wanting to return to classical physics. And in fact, the real motivation is a demand for clarity and precision. Now, some people may identify clarity and precision with classical physics. If that's what you mean by classical physics, then I'm all for classical physics. Here's Bell's first Bell quote. Conventional formulations of quantum theory, and of quantum field theory in particular, are unprofessionally vague and ambiguous. Professional theoretical physicists ought to be able to do better. Bohm has shown us a way. Now, hidden variables. Yes?
I guess hidden is a bad word because actually Moore mechanics position of the particles is the only parameter that determines the outcomes of the measurement. So it's the only physical quantity that in quantum mechanics we can measure.
It's even more than that, but you're right. The realization that von Neumann's proof is of limited relevance has been gaining ground since the 1952 work of Bohm. However, it is far from universal. Moreover, the writer, that is Bell, has not found in the literature any adequate analysis of what went wrong. Like all authors of non-commissioned reviews, he thinks he can restate the position with such clarity and simplicity that all previous discussions will be eclipsed. This was from his hidden variables, first hidden variables paper. Maybe it was his first paper on foundations of quantum mechanics. And that led him to the issue of non-locality, in which he said, this is from the same paper, because it was a hidden variables paper about hidden variables, he did look at basically the only hidden variables theory on the table at the time, Bohm's theory. He studied it, he looked at it, saw how it fit in with the no hidden variables theorems. And he said, in this theory, an explicit causal mechanism exists whereby the disposition of one piece of apparatus affects the results obtained with a distant piece. This is strange, of course. Bohm, of course, was well aware of these features of his scheme and has given them much attention. However, it must be stressed that to the present writer's knowledge, there is no proof that any hidden variable account of quantum mechanics must have this extraordinary character. It would therefore be interesting, perhaps, to pursue some further impossibility proofs, replacing the arbitrary axioms objected to above by some condition of locality or of separability of distant systems. And you've heard an enormous amount about that, what the upshot of that, of the ensuing analysis of Bell led to. He got much more than he bargained for. He wanted to see if he could show that it was, whether or not it was, he wanted to show it would be impossible to have a local hidden variables theory. And he showed it was impossible to have a local theory at all. Nature is non-local if it's governed by quantum mechanics. Now, the notion of a quantum theory without observers was crucial to Bell, and it's been explained to you by many speakers what that means. It is not, the idea here is, of course, not that we don't want to have observers in physics, observers in the real world, and physics better account for the fact that there are observers. But observers and measurement and vague notions like that, and not just vague, but even macroscopic notions, they just seem not to belong in the very formulation of what you would could be regarded as a fundamental physical theory. So, and this is advice to you, if you see some proposal for a new interpretation of quantum mechanics, it will often be very complicated, and you will want to understand whether it's viable or not, it has much merit or not. If you see that it involves axioms about measurement, you can probably save yourself a lot of trouble by just saying, this just doesn't address the problem. There should be no axioms about measurement. And I have found that, by and large, physicists have enormous trouble appreciating this demand. They just can't get away from axioms about measurement, as simple as a demand, despite that it's a very simple demand. Here's Bell. The concept of measurement, bad word, becomes so fuzzy on reflection that it is quite surprising to have it appearing in physical theory at the most fundamental level. Does not any analysis of measurement require concepts more fundamental than measurement? And should not the fundamental theory be about these more fundamental concepts? Bell goes on. It would seem that the theory, quantum theory, is exclusively concerned about the results of measurement and has nothing to say about anything else. What exactly qualifies some physical systems to play the role of measurer? And many of the quotes I'll be using here were used before. If, in fact, there's some repetition, you should take that as a sign that these are really important quotes. Lots of people are using them. And be sure, all the more certain to try to make sure you understand them. By the way, I don't expect that just if you haven't really studied these quotes and studied Bell, I don't expect that you would instantly understand them. But what I would insist upon is that you should try to understand them and get yourself to a point where you do understand them. And that's part of why what I consider the value of what I'm doing here. I'm telling you that these are things you need to understand, whether you understand them entirely now or not. You will understand. You will be rewarded for the effort you make in trying to understand these things. Okay, was the wave function of the world waiting to jump for thousands of millions of years until a single-celled living creature appeared? Or did it have to wait a little longer for some better qualified system with a PhD? If the theory is to apply to anything but highly idealized laboratory operations, are we not obliged to admit that more or less measurement-like processes are going on more or less all the time, more or less everywhere? I think Lev denied this at lunch today, but okay. You're not going to object now because we went through it at lunch and everything's on the table. Do we not have jumping then all the time? Now let me make a remark about the measurement problem. Of course, Bell wrote a great paper on the measurement problem called Against Measurement. I don't have really any quotes from there, although there could be many quotes. The point I want to make is, what I emphasize is the connection between the measurement problem and the idea, the demand that that any fundamental physical theory, and quantum theory in particular, be a theory without observers. That the axioms of the theory don't refer to measurement or observation. That would say that if we try to analyze quantum theory, textbook quantum theory, all of the axioms which refer to special things happening during measurements should be ignored. We should only take seriously, or try to take seriously, the axioms which just refer to what's happening regardless of whether a measurement is taking place or not. That is Schrodinger's equation. No reference to measurement in Schrodinger's equation. Well, when you analyze what happens to the wave function of a system and apparatus during Schrodinger's equation and don't invoke any measurement axioms, you get these unpleasant superpositions which are the measurement problem. How do you understand from these crazy wave functions, which are superpositions of different macroscopic situations, what is that? What do you understand that that's telling you about the world? That's the problem. You would like, what quantum theory should explain are certain patterns of macroscopic events, the things we see happen. And in particular, it should explain the statistics of results of quantum experiments, pointers pointing this way or that way. And in particular, it better be the case that pointers end up sometimes pointing. Whenever you do the experiment, you better get results. Those results are not in the wave function. We're insisting that we can't invoke rules of observation to explain those results. So how do we explain that a pointer ends up pointing? It has to be the case that the basic variables of the theory are such that they will correspond when the variables have appropriate values to pointers pointing and things like that. Now, the basic variables should be presumably variables describing the microscopic scale, because big things like pointers are made out of small things on the more fundamental level, the microscopic level. So there should be variables on the fundamental level, on a microscopic level, which, when they're arranged in a certain way, these constituents form objects like pointers which suitably point. That leads to the need for local beables, structures in space-time, local structures which can be arranged so that we have tables, chairs, and pointers and all the rest. Here is a statement of Bell about local beables. This was used before. What are they? These are the mathematical counterparts in the theory to real events at definite places and times in the real world, as distinct from the many purely mathematical constructions that occur in the working out of physical theories, as distinct from things which may be real but not localized, like the wave function, as distinct from the observables of other formulations of quantum mechanics for which we have no use here. I don't know whether you detect any edge in what Bell says in this last part when he refers to observables, but I think there's an edge there, and I'll come back to that very soon.